All right, here we are with the app again, and I'm going to just very quickly give myself 10,000 simulations. And I'll go ahead and give myself another 10,000, and another 10,000, and another 10,000. You can see down at the bottom, I've done 40,000 simulations so far. Each time, I was grabbing 71 students from a population where 1/4 prefer the front, half prefer the middle, and a fourth prefer the back. And every time I computed the chi-square statistic. And only 2.9% of the time did I get a chi-square statistic that was at least as big as the chi-square statistic from the data in the TigerStats M111 survey package. In the actual data, I got 7.03, but most of the time my chi-squareds were less. Only 2.9% of the time were they bigger than or equal to 7.03. That's my p-value in this test of hypothesis. And so this time I would say, looks like we got pretty strong evidence that seating preferences at Georgetown are not 1/4, 1/2, 1/4. That there's something different, maybe less than a fourth preferring the front and a less than a fourth preferring the back. That's the way the data was going anyway. Okay, so that's the recap of using the app from the previous part of the slides. I'll go ahead and leave it now. Now, you're not going to use an app every single time you do this test of hypothesis. The chi-square test for goodness of fit is available as directly as a function in R. And the function's name is chisqtestGC, okay? So for the gambler study, here's how you would set it up off of this summary data. You're going to have to use the C function, and don't worry, in DAs and things like that, I'll kind of tee you up to do this. You don't have to memorize how to do it. Use the C function to stick together the 6 numbers that you have in the gambler die study, separated by commas, as you see. And you can give names to those numbers as you go. And that's the observed tally table. You also need to set up a vector of the null probabilities for each of the 6 sides of the die. And that's what's happening here in null probs. And then you'll head to chisqtestGC, where you throw in the table of observed counts. The P you're familiar with from other inferential types of functions. It talks about null value. The null hypothesis thinks the chance of each side is, 1/6 each time. And those simulations we saw being done in the app, those can be recreated with this function if you set simulate.pvalue to true. You need to say how many simulations you want to do. I suggest several thousand. Please don't do a billion. 3 to 10,000 is fine for the RStudio server to handle. You can get a little graph of how the simulations come out if you say graph is true. So let's give this a try here in RStudio. And I think I might need to library TigerStats, so I'll get that done. And I think I want to move myself somewhere else. Okay, I don't want to enter the code. And lots of stuff happened. But here's the observed vector. The 8, the 18, the 11, the 7, the 9, and the 7. Just to show you observed another way, I'm going to type it out at the console at the bottom. You can see the names. And the null probs is just 6 1/6s. Approximated here is 0.167. Okay. You also have the chi-square test procedure out here in the console And we're going to look through it bit by bit, all this stuff from here to here. And you've got a graph down here. So we'll talk about the significance of those as we go through the slides. So the output starts off with identifying what you're doing. The chi-square test is often called Pearson's chi-square test after the person who invented it. And we're simulating the p-value like we did in the app. Now, the table that comes after gives the observed counts, what we saw the gambler's die actually do, the table of expected counts, and the contributions that come to the chi-square statistic when you do those computations. Remember the 8 minus the 10 squared divided by the 10, and so on. The chi-square statistic itself, that's our test statistic, it's 8.8. Degrees of freedom of the table, we'll talk about what that means later on. But there's the p-value. Again, it's about 12% like we saw in the app. And so you can make a judgment based upon that we don't have strong enough evidence here to rule out the idea that the die might be fair. Now, as far as that graph you saw, it's a graph of the 3,000 simulated p-values. So we'll histogram. The red line here is at 8.8. And you can see a good portion of the histogram, about 12% of it, is past 8.8, suggesting that about 12% of the simulated p-values were bigger than 8.8. So 8.8 is just not that unusual to get if you're rolling a fair die. You can do the same thing with the seeding study, except here the data is inside a data frame, so you don't have to make one of those summary tables. You just say, I want to look at the variable seed. It lives in N111 survey. The null hypothesis thinks this, and we'll simulate p-values, 3,000 of them. So let's give it a try. And we have some results in the console to look at, and we have a graph over in the plots window. And so this time, all in a flash, R not only recorded the results that it found when it looked down the seat variable in N111 survey, it recorded how many students you would expect to see preferring each of the different types of seats if the probabilities were really 1/4, 1/2, and 1/4. And based on that difference between the table that you see versus the table that the null expects, you can compute contributions to the chi-square statistic and add them up, and they turn into that 7.0282. The chance of getting a test statistic at least that big, if the null is right, is only 3%. And so now we have fairly strong evidence that student seating preferences at Georgetown College differ from the available seating somewhat. So far, we've been estimating these p-values by doing a lot of simulated resampling, either with the app or with chisqtestGC. But when the chi-square test was first invented, nobody had computers. It was invented before the year 1900. And so certainly there was no chance to do these kind of simulations to estimate a p-value. What was used was a mathematical curve that leads to what we call the chi-square approximation. So here are some facts about the chi-square statistic. They're math facts that were known a long time ago. They were figured out when the chi-square statistic was discovered and developed. The basic fact is that if you have a large enough sample, like if you roll the die enough, or if you survey enough students like we did with Math 111 survey, and if the null hypothesis is true all along, then the expected value of the chi-square statistic is going to be equal to It's degrees of freedom. And you wonder, what is the degrees of freedom? The degrees of freedom for a chi-square statistic is one less than the number of cells in the tally table. So for the gambler die, 6 cells, 6 faces of the die. Degrees of freedom would be 5. For the seeding problem, 3 different answers, front, middle, back. Degrees of freedom would be 2, 1 less than 3. So you can expect, if the null is right, you can expect the chi-square to be about the degrees of freedom. Give or take standard deviation of square root of twice the degrees of freedom. So, for example, for that seeding study, if the null is right, you'd expect the chi-square to be about 2, give or take square root of twice the 2. That's square root of 4, that's a 2. So you're expecting around 2, give or take 2 or so for your chi-square statistic, and instead you got 7, which was several of the standard deviations above the expected value. So that suggests the chances of getting 7.02 or more, if the die is fair, are really kind of small, as indeed they turned out to be. So you might kind of wonder, though, how big is a big enough sample for these facts about the chi-square statistic to really hold and to come into play? And the general people looking around at simulations have generally decided that if the expected counts in each cell is at least 5, then the sample is definitely big enough. No worries at all. It's actually okay for some of the cells to be less than 5, maybe 20% of them, or to be less than 5, but definitely not any of them like less than a 1. But you can go a little further with your facts. If the sample size is big enough, the chi-square statistic as a random variable behaves a whole lot like what we call a chi-square density curve, with degrees of freedom equal to the number of cells minus 1. Let me just give you an example of that to show you such a curve. Let's do chisqtestGC with the variable C, living in Math 111 survey, null hypothesis like it was before, graph is true. But this time it doesn't say simulate.p.value. We're going to actually use the chi-square curve with 5 degrees of freedom to get our p-value. So we try it out over here in our studio. And heading back to the slides to analyze it, all of the output in the console is the same, but the p-value is being gotten by this graph you saw in the window. The chi-square curve with 2 degrees of freedom looks like this thing sloping down. And here's 7.03, the chi-square statistic that we got. That shaded area is about 0.03, like we got in the simulations. So that's how people in the old days found p-values. They just happen to know as a math fact that the probabilities for being past a certain number for a chi-square statistic are about equal to the areas underneath these curves. So the basic summary here is that the chi-square statistic, the chi-square test for goodness of fit is a nice inferential procedure if you're studying one categorical variable. And if you've got somebody who claims that that categorical variable is distributed in some specific way, like the gambler saying each of the chances for each of the faces is 1/6, or somebody saying preferences for Georgetown College students match the available space, 1/4, 1/2, 1/4. The specific statement about the chances or statement about the distribution of that categorical variable, and they become the null hypothesis in a chi-square test. If your sample got big enough so that the expected counts in each cell were at least 5, then you don't have to use simulation to approximate a p-value. You could use the chi-square curve that R works with for you to approximate the p-value. But if your sample is not big enough, just go ahead and use simulation. Simulate.p-value equals true, set the number of simulations b to several thousand, and go ahead. The chi-square test is a test of hypothesis, so it has the same 4 basic steps. The prepare step where you state the hypothesis. But you don't really have to spell out the parameters all the time. Like with the gambler's die, instead of like laboriously saying chance of a 1 is 1/6, chance of a 2 is 1/6, all the way down to a chance of a 6, you could just say die is fair. Sometimes you do have to say each of the probabilities for each of the outcomes. Then you check to see if the expected cell counts are at least 5, and you're going to find that R does that for you because it's computing those expected cell counts and showing them to you in the output anyway, so you can just look at them. And the calculate step is being done by R. That's where it calculates the chi-square test statistic and the p-value. And so you can use that p-value to decide about the null hypothesis and write up a little conclusion about how much evidence the data you have provides against the null hypothesis. So that's all for our slides. We'll be talking in class about the DA and taking questions on it, I'm sure. See you later.